Good morning. Thank you for coming. This is the HPC and Big Data and Data Science Dev Room. We're very happy to organize this Dev Room this year. So I will briefly introduce the organizers. Kenneth here from University of Ghent, Roman from People Lab, and the Apache Software Foundation, and well, Ewan is not here, and myself, I'm from KTH in Stockholm. So today we're going to have a mix of talks from big data, HPC, data science. So we had really many submissions. We had 48 submissions, and we only accepted, well, we did our best to accept as many as we could, so we're going to have 20 talks, so 20-minute talks and 5 lightning talks. So we'll start right away. We have a lot of things to present, and I'm very happy to introduce Theodore from Apache, who's going to talk about machine learning.
So, hello everybody, thanks for coming so early, even after the Saturday, I guess after this stuff. So, I'm a researcher at the Swedish Institute of Computer Science, and the past year I've been working on Flinkml, which is a large-scale machine learning library for Apache Flink. So, to start, I would like to focus a bit on what we mean by large-scale machine learning and why we need it, and maybe to clarify a couple of things. So when people talk about large-scale machine learning or big learning, the very common thing that we hear is talking about the data size. So we have big learning tasks when our data is so big that it cannot fit into the memory of one machine, or a model is so big that it cannot fit into the memory of one machine. But they never say which machine. So for me, it's very important to clarify that the size of your computer is not an intrinsic property of the data. So that's not a good definition. If we want to be precise, we shouldn't be using our current computing capabilities in order to define our learning tasks, but rather we should be talking about specific learning tasks. And that way we can differentiate between small-scale and large-scale learning. And we have small-scale learning when the active budget constraint that we have is the number of examples. So in cases where the data is limited and obtaining it is costly, we would have a small-scale learning task. On the other hand, we would have a large-scale learning task when our active budget constraint is actually the time. So you can imagine in any kind of big data scenario, we have so much data that we don't really need anything else in order to do our learning. However, we are limited from the time. As such an example, you can think of a company like Spotify. Let's say that they want to provide recommendations for all their users every day. Now, if that computation takes 1.5 days, that is useless. So what they have is an actual time constraint there. They need to be able to make their answers work within the time that they have, despite of the millions and billions of data points that they might have available. And this is the type of learning that concerns us with Flinkml. So before diving into Flinkml and the large-scale machine learning issues, I would like to introduce Apache Flink very briefly, for those not familiar with the platform. And for those that want to learn more, there's a talk coming up at 4 p.m. here by Till Roman that's going to delve into more details about the engine. So Apache Flink is a distributed data processing platform with a streaming data flow engine at its core. It provides powerful and easy to use APIs for streaming and batch processing. And it's a technically advanced engine that has a number of features that make it very good for large-scale machine learning tasks. So here we can see the Flink task. It works well within the Hadoop ecosystem. It can use many data sources. It provides high availability through Zookeeper. And on top of the data and stream processing APIs, it provides a number of libraries, like Jelly for graph processing, the table API for SQL-like queries, and Flinkml, which is the machine learning library. So what makes Flink a good platform to use for machine learning? So we'll take a brief look into some of these features that make it a good candidate. So first, it's the Flink API that provides a functional style programming, maybe with some SQL-like commands like group by, for example. And this allows for the quick development of and prototyping of machine learning algorithms, and the programmers get a familiar paradigm to write their programming that is also intuitive. And at the core of Flink lies its streaming data flow engine. And using this engine, we're able to set up a set of operators at the beginning of deploying a job and then continuously pipe data through without having explicit processing stages. So this type of engine makes real-time stream processing possible in Flink. And what it also does is that it provides us with native iterations. And native iterations allow us to write certain programs, like most machine learning programs, without materializing the intermediate. And when compared in fact with the batch engine, like for example Apache Spark, each stage has to be submitted at the end of each iteration, and that creates additional scheduling overhead. Now what we are able to do with Flink instead is that we are able to maintain a partial solution. So you can think, for example, your machine learning, the model of your machine learning algorithm is a partial solution, and we're able to iteratively update it within the same data. Now in addition to batch iteration, Flink also provides us with delta iterations. Now what delta iterations do is that they allow us to shrink the size of the problem as we near its solution. And this is something that is very useful in cases like graph processing, and it could also be, the same principle could be applied as well for machine learning problems. So with that in mind, let's take a look into Flinkml. So the development of Flinkml started last spring, and the first version was released with version 0.9 of Flink. And I should mention that it's written completely in Scala. So the library was designed with three goals in mind. The first one is to be truly scalable. So we want efficient algorithms and communication efficient algorithms that allow us to actually scale the processing that we do with web scale or societal scale data. The second one is the minimization of glue code. And when we talk about glue code, we mean all the code in a machine learning program that is not machine learning. It's the thing that ties all the things together in order to make it work. And according to a recent publication from Google, a mature machine learning program might end up having 95% glue code and only 5% is actual logic. And what we try to do with Flinkml is actually try to minimize the amount of glue code that developers need to write. And the third one is ease of use. We focus on having familiar and easy to use APIs. We want to provide good documentation and examples and support for the users. So they're able to jump right into writing stuff. So we'll take a look at some of the algorithms that are currently available on Flinkml. So starting with the supervised learning, we provide generalized context optimization framework. It currently has an implementation of stochastic gradient set that you can use for any learning task. We provide support vector machines and multiple linear regression as well. And we also have a highly scalable ALS implementation that scales to data sizes that companies of the size of Spotify might have. And the growing set of common pre-processing algorithms for machine learning tasks. And the one feature that we took care to include from the beginning was the support for machine learning pipelines. And these allow us to develop complex sequences of machine learning tasks with minimal glue code. So with that, we can take a brief look at the API. So we can see how easy it is to write a small machine learning program with Flinkml. So if using the standard Flink data processing commands, we can just read a training and a test set. And then we can quickly create a set properties for our learner. And you can see that we have some familiarity at least with the scikit-learn programming library, the machine learning library, that which we do in order to provide our users with more familiarity. We can call fit to train the model, and once we have done that, we can just start using our model in order to make predictions. So we can see that in less than 10 lines of code, you can actually have a fully working, simple learning system that will scale with your data set. And I would also like to demonstrate how easy it is to create a machine learning pipeline. So what we will do here is train a regression model after passing our data through a standard scaling algorithm, and then augmenting our features also with a third-degree polynomial. So our pipeline is simply created by chaining together as many operations that we need. We start with our scaling, we chain the polynomial features transformer, and then finally we chain our predictor. And once we have that pipeline, we can treat it as any other learning. So we can just call fit on the pipeline itself, and it will actually pre-process all the data with all the transformers that we have used previously and do the training. And the same applies for prediction. When we pass a testing data set to the pipeline, it will actually transform and perform all the transformations that we have ordered in our pipeline in order, and then actually use the prediction. So next, I would like to look at some of the cutting-edge machine learning algorithms that we have implemented in Flink in order to make it a truly scalable platform. So first, I would like to talk about a relatively new communication efficient optimization algorithm. So stochastic gradient descent, or SGD, is perhaps the most widely used first-order optimization algorithm that is out there, and it's very popular in areas like deep learning that have seen a major resurgence now. And SGD's strength comes from the fact that it's actually very simple to implement, and most distributed implementations use a very simple synchronization scheme as well. At the end of each iteration, we sync all the workers and then move on to the next one. That has a high communication cost, and it also includes slow updates to the model only at the end of the iteration. So we can do better than that. So COCO, or Communication Efficient Coordinate Data, is an algorithm by Yagi and others at Berkeley. And this aims to reduce the communication costs in an optimization problem and achieve faster conversions. And it uses a number of tricks in order to achieve that, and we will see a couple of them. So first one, it moves from the primal optimization problem to the dual one. So the framework of dual optimization is conceptually simple. So what we do is that we transform our original primal minimization problem into a dual, which is a maximization problem. So once we do that, what we have actually is that the dual provides a bound for the primal problem. And by having this bound, it's very easy then to have a stopping criterion when to stop iterating. So here's an example with a regularized regression problem. We take the primal minimization problem, we transform it into a maximization problem using a property that is called the Lagrange duality. And for such problems, coordinate descent methods have been used for large-scale problems, and they give stronger convergence guarantees at the same iteration cost as SVD. They also require no step size, which is a major parameter that you need to set for stochastic gradient descent. And it gives us, due to the duality that we have the bound, it gives us a very well-defined stopping criterion for our iterations. And another thing that we do at the stochastic gradient descent is that we update our model finally either at the end of each iteration or at the end of our run, actually. So by syncing all the workers. So that means that a lot of the workers might end up working with a stale version of the model for a very long time. So in COCO, the updates are happening locally within the workers without any communication, meaning that the workers have a very fresh model that they're iterating on. They only sync as little as possible at the end of each super step, let's say. And that also reduces the communication cost. So this is basically an illustration of how COCO works. Each worker is a small dual optimization problem. And at the end of its local iterations, it communicates only the update vector that it needs to the other workers. And we start then the next super step. And this reduced communication as part of optimization can have great effects for the convergence rate of the algorithm. So COCO here is the red line, and the log we have a log scale here. So it gives stochastic gradient descent and coordinate descent by sometimes orders of magnitude in terms of performance. And this is what we use in order to perform optimization for support vector machines in Flink. So definitely COCO has a good performance, but it has one important disadvantage, and that is the barrier synchronization that we mentioned. If you have a straggler in your cluster, which is a machine that is working much slower than the rest, that means that all the faster workers need to wait for that straggling before moving on to the next iteration. So there is a way to deal with that as well, and that is recent from last year that is coming out from CMU by Professor Eric Zink. And it deals efficiently with stragglers and achieves actually great performance. So we can take a look at the different synchronization schemes that are available to us. So the first one is block synchronous parallel. In this model, as we mentioned, at the end of each iteration, we wait for everybody to finish and then we move on to the next one. And of course, this can have an adverse effect on the speed of the convergence of the algorithm. Another option is to do something asynchronously, and we let every worker work on its own, and we don't really sync, and we just obtain the solution by combining them all at the end. So this is possibly fast, but it can also lead to diverging solutions because many workers can have very different versions of the model, and that can result that we just diverge and we don't arrive at any solution ever. So as a compromise between the two is to have stale synchronous iteration. So with stale synchronous iterations, what we do is that the fastest workers can only be up to k iterations ahead of the slowest one. And if they are about to move further ahead, we stop them and we tell them to wait until the slowest one gets caught up. So this allows the faster workers to work and update the model so we achieve faster convergence, but ensures that the slow workers will not fall too far behind in order to make sure that the algorithm will converge at the end. So taking a look graphically, so here worker 1 is the fastest one, and if it manages to reach iteration 7, since we have a stainless threshold of 3, it will actually have to stop there and wait for worker 2 to catch up before moving on to the next iteration. So here we can take a look at the performance of stale synchronous in Flink. So the blue line is actually bulk synchronous, and what has happened here is in the cluster at any point in time, one of the nodes has generated load of 100% for 12 seconds. So that means that we basically have a straggler in the system that we create. And we can see that by using the stale synchronous parallel iterations, we're able to converge much faster than using the bulk synchronous parallel, and they also achieve actually better optimization in the end. And this will soon be merged into Flink and Flinkml, and when that happens, it will be, to my knowledge, at least the first general purpose data processing platform that supports stale synchronous iterations. And so finally, I would like to talk about some more work that is currently being done in Flinkml and what we have planned for the future. So currently we have all the tooling in place for the performance evaluation of the model as well as the cross-validation, and we're working on making it easier to persist your models and export them in a TML language, for example. And all of these things are pending pull requests that we hope to be able to merge soon. And for our long-term plans, we include two main areas. The first one is streaming and efficiency. So for streaming, Flink already has Samoa bindings, and Samoa is perhaps the most popular online analysis platform out there currently. And our plan is to actually kickstart streaming machine learning library that will include a number of machine learning algorithms in there. And the other area of focus for us would be computation efficient algorithms. So the question is, how can we scale learning into societal scale data sets, but using only modest computing resources? Because not everybody is Google, not everybody has data sets with 10,000 machines. So this is a major challenge for us, and we plan to use a lot of knowledge that is coming from the HPC field in terms of efficient computation, using GPUs and the like, in order to make sure that we're actually using all our hardware to its maximum potential. And this is it for me. Please check it out. You can go to flink.apache.org to find more about Flink, and this is the link for our documentation. Thank you.
We have time for maybe one or two questions.
2 weeks ago, I attended a UC Berkeley session on the updated version of the Coco.
So that takes care of some disadvantages of the original Coco algorithm. It didn't scale well if you increase the number of machines that you were using. So the Coco Plus uses, I think, adding instead of averaging in order to solve that kind of problem with the scaling. And it is planned for us to actually use that. Because currently, after 20 machines, Coco does not actually perform that well.
Any other questions?